Hey there. In this video, we're going to be talking about the definition of a derivative mathematically. Now, in the last video, I explained kind of like what a derivative was, like explained how it looks on a graph and theoretically, and how to conceptualize it. But here we're going to talk about like the literal algebraic definition of the derivative, and there is a formula for it actually for calculating it. And that formula is actually a limit. So this is why limits are important. Remember in the last video when I said that derivative was essentially as we approach a specific point, like when we had the change in y over change in x, just making the change so infinitely small for each of them until we finally got to what that value was at a specific point. Well, we can also do this with limits. Like a limit is just an easier way to find the value as it approaches a specific point, like as we approach a specific point. So the idea is going to be as x approaches whatever value of x that is, what is the limit or what is the derivative? So that's kind of what we're going to get into today and how the formula looks. So we're going to kind of turn it or make it or transform it, you could say, morph it, mutate it, whatever it is, from the change y over change in x. So remember when I said that average rate of change has its own formula? Remember what that formula was? Rate of change. Yeah. If you went to middle school, you know this one. It is m equals change in y over change in x. And that's our rate of change. Easy as pie. So we're essentially going to be doing the same thing, but at a specific point in time. So that's our instantaneous rate of change, if you remember from the last video. I was going to write instant rate of change. Rate of change. Instant rate of change. Now, it would look like this. Problem is, it has to be at the instant. So we're going to make it a limit as x approaches a, change in y over change in x. That's essentially what it's going to be. And since it looks a little weird just to have change in y over change in x, what this becomes is what the change in y over change in x is, which is y2 minus y1 over x2 minus x1. Now, we're going to go a step further and transform it again. What does this actually look like? It could be written as f of x minus the second f of x, but we're going to call it a. So, like the value of 1 or x1 or y1, sorry, is going to be a. So x1 is a. And on the bottom, what's the change in x? It's going to be x minus a. Remember that I'm using a as a placeholder because I don't actually know what value of x I'm using because we don't have a situation. We can use this once we're in a specific situation. And then we'll replace a with whatever value of x we're looking at. Example being, like if we're on a graph and I have this, I'm like, okay, find me the derivative at x equals 10. Boom, x equals 10, that's our a value. So the idea would be as x approaches 10, what's the value? That's our derivative. So this is our first formula, actually. I'm going to erase all this. Formula, definition, I mean, they're interchangeable, I guess. Cross this out, and we're going to write lim as x approaches a, f of x, or the y2 minus f of a, y1, over x2 minus x1, or x minus a. Can you see that okay? There's a light on it, but that's okay. Okay, so this is the first definition of a derivative, and I hope you can see how it relates to that. Now you can plug any function into this. The way it works is since we're working with a limit, we don't exactly have specific values on a graph that we can plug in for our x2 and our x1. What we do is we plug in the actual function into this equation. Hello. We plug the actual function into this equation, and then we solve it as a limit. And it can get really wonky. Like, say my function was like 3 cosine of 5x. What do? Well, I plug it in. And assume I'm doing, like, as x approaches, I don't know, like 8. So it'd be like this. As 3 cosine 5x minus 3 cosine 5 times 8, because that's x, or the x that we're approaching. Or as x approaches 8, and a is 8. And then we're going to divide that by our change in x, and that's just going to be x minus 8. So lim as x approaches 8. And then we solve this. And I'm not going to go the next step on this specific problem, but I hope that illustrates what is actually happening. Hi, bye. We plug in the actual equation, or f, the function. We subtract the function evaluated at that point, and then we do the x2 minus x1, or just x minus 8. So to finish it, to actually find the derivative at that point, the numerical value of the derivative, you would follow through, you would evaluate the limit here. Essentially what you do is, I hope you remember, you get it to where you can substitute 8 into the equation without 8 dividing by 0 on the bottom, and then boom, you're good. But I'm not going to solve that right now until the later problems, which get really, really weird. But like I said, you can use any equation on this. It can be quadratic, it can be cubic, it can be logarithmic. Whatever you want to do, you put this in. And I know it looks really messy right now, but this is the actual theory behind it, like why, or how we're able to find the slope at a specific point. Okay, now we're going to go into the other definition of a derivative. So this is the first one, and this is used for finding the actual value of a derivative at a point. As you saw in it, like as x approaches a, and we get to choose what value of a that is, it's because derivatives evaluate at a specific point. But if you remember from the last video, when I took all the derivatives at points and then put them on a graph, like remember the quadratic that was right here? The second definition of a derivative, or formula to find a derivative, gives us the function of the derivative as opposed to the value at a specific point. So we can use it and we can get the function, and then we'll have a formula or a function that we can plug a value of x into to get the actual derivative back at that specific point. Now, this is very similar to what there was before, or to this one, but instead of, having a value of a, we're not trying to evaluate at a specific point. We're just going to make an equation or a formula, and then we're going to simplify it as far as we can, and that's going to be our derivative. And it is still going to be a limit. But instead of as x approaches a, it's going to be as h approaches 0. So we're going to start like this formula 2. Lim, so I'm going to change colors just for kicks. Boom. Lim as h approaches 0, we're going to have f of x plus h minus f of x. Oh, we're getting messed up there. And then we're going to divide by h. Now, why is this? Why are we substituting h for a bunch of random values in here? We're pretending that this is the change, that h is the change in x, or yeah, the change in x. And we're approaching 0 just because it's a nice little placeholder. This is like a modified version where we use placeholders that are variables to keep it abstract, because we're trying not to evaluate at a specific variable. We want to be abstract so we can get an equation as opposed to a value. And so h is far from 0, and h is like the distance from 0. So if we had x minus a, we could pretend like that's just h. We're going to pretend that's h. H is a made-up variable. It has no value, actually. And in the end, we're just going to be substituting it for 0, or 0 for h, when we try to evaluate the limit. So what would this look like? Well, it's exactly the same. You plug x plus h into whatever equation you want. Let's pretend that our equation is like 3x to the fifth. Well, what does this look like here? First, it's going to be limit as h approaches 0. Well, our function f of x is equal to 3x to the fifth is going to be 3x plus h to the fifth minus 3x to the fifth all over h. And then you evaluate it. You don't necessarily solve, you just evaluate the limit at, well, at h equals 0. And so you just simplify, you have to multiply all this out, and then you subtract 3x to the fifth, and then you multiply or divide everything by h that can be divided to get h out of the denominator, so you don't divide by 0. And then you substitute 0 for h, and then you just take the remainder of that, and you have it. And I'm just going to jump ahead real quick. I'm going to look like a wizard because I can do it all in my head at once. It's going to come out to be 15x to the fourth. Does that make sense? If I take this and I evaluate the limit, it's going to give me an equation. And that's going to be the derivative, or the equation of the derivative, I mean. And it's nothing more than that. These two equations, or you could say definitions, are how we can find a derivative. Remember, this first one gives us the numerical value of a derivative at a specific point, that point being a. And this one, the second one, where as h approaches 0, function, or the function of x plus h minus f of x all over h, that actually gives us the equation. Because in the end, h is just going to disappear from our answer, and it's not going to be around anymore. Anyways, I hope that makes sense. If you don't want to see any examples, you can stop the video right here, but we're going to do some examples now. These can be tedious, and I need the practice, so you're just going to have to bear with me. Boom, boom. I'm going to rewrite these. What happened? Yeah, I have an audience. Okay, what's a good place? Right here. That's where I am. So, as x approaches a, we're going to have f of x minus all over x minus a. And the second one is h approaches 0, f of x plus h minus f of x all over h. Stop recording. Okay, thankfully we were recording. I thought it'd stop recording. I thought I'd never press start for a second, but I did, and that's what counts. Okay, first problem, I have them written off here to the side so I can just reference them. The first one is going to be 1 over x squared to the 64. So, just get my color out. It's going to be using the definition of the derivative. And there's a reason it says definition, because there are a lot of shortcuts that we're going to get into in later videos, which are so much easier. Using the definition of the big D, the derivative, find the derivative of limit, no, not limit, it's f of x equals 1 over x squared minus 64. Okay, So the actual concept of the derivative right here is actually really simple. You don't have to do a lot. The trouble when in solving this is going to be how good your algebra is. So your algebra better be on top of things, or else you're going to struggle, like I did. Anyways, so all we have to do is we just have to pick the equation that we're going to use and then plug it in. Now, what are we doing? And I'm going to talk like Dora the Explorer here. You don't have to talk back. You choose, are we going to... I'm lost. I made a joke and now I'm lost. Uh, are we trying to find the value of the derivative, or are we trying to find the equation of the derivative? Answer, we're trying to find the equation of the derivative. If I wanted to find the value of the derivative, the question would have said, like, find the derivative at x equals, and then some number. But that's not what we're doing. So we're going to use the equation with h. It's going to look something like this. First, it's a limit as h approaches 0. We're going to have f of x is the first one, and that's going to be 1 over x plus h squared minus 64 minus 1 over x squared minus 64, and then all of that over h. Now, if you know anything about algebra, you can see immediately how tedious this is about to get for us. So, step number 1, we have to essentially combine the terms. And so both of these are going to become is multiply by both. This one's going to become multiplied by x plus h squared minus 64. This one's going to be multiplied by that. So it's going to become x squared minus 64 over x plus h squared minus 64 times x squared minus 64. Minus x plus h squared minus 64. Boom. Times, oh, not times right there, it's on the bottom. And it's just going to be the same thing, x plus h squared minus 64. X squared minus 64. So, let's multiply it out. Oh yeah, then it's all over h. Let's come over here, part 2, that's going to be 1, that's going to be 2. So we already have x squared minus 64. Now we're going to multiply this out. It's going to be technically minus right here. X squared plus 2xh plus h squared minus 64. And remember, it's all that is inside of big parentheses. And we're subtracting it. I'm not gonna write the denominator of the top or the bottom. I'm just gonna solve this. It's gonna become x squared minus x squared right there. So we're gonna cross that out. Negative 64 minus negative 64 is gonna cross that out, become 0. We have negative 2xh plus, well, there's no h squared on the outside to get rid of it, so it's just going to be minus h squared. And now we can put it in its little happy little denominator. I'm not multiplying this out. X plus h squared minus 64. X squared minus 64. All over h. So what we can technically do is we can, using our algebraic rules, we can take this denominator, we can move it down here, and then all of a sudden we have, just gonna move it like that, h, multiplying that. And what we can do now is we can cancel out h. So h, h, h. So negative 2x minus h over x plus h squared minus 64 over x squared minus 64. So tedious. And now we can substitute h in for all our other stuff. So negative 2x minus h is just going to be negative 2x over this behemoth that you see right here, which actually I have to write out. It's going to be x squared minus 64 times x squared minus 64. It's going to be simplified down to x squared minus 64 squared. Boom. Now I'm going to double check and make sure this is the correct answer, which it should be. Oh, I suppose I forgot to mention why I did this. At this point, we can remember that it's a limit as h approaches 0. So all we have to do is, now that we have h out of the equation, that's where I was going with this. Like, the purpose of all this mathematical gibberish was to get it to a point where I could get h out of the denominator to substitute the limit value back in. So h equals 0, substitute h in for this, x squared minus 64, and it's not undefined because the denominator makes sense. We just cancel out, and then this is what we have after we substitute 0 in for h. Now I'm going to head over here and double check. Question 8. Yep, that's exactly what it is. Negative 2x over x squared minus 64 squared. Do you see how tedious that was? It kind of sucked. But that's the theory of it. You just plug it into the formula, like I had right here, I was just about to erase. You plug it into the formula, you do all the math, and then you get what you want, which is funny letter, A+. Anyways, I had another example lined up, but I think I've reviewed enough, and I don't really want to go through the tedium of that second one. But the concept remains the same. It's, you just plug it in, and then you hope that your algebra can bear the weight of all that pain.